And continuing with homework number 6 for physics class, here's problem number 4. We have a semi-truck trailer or semi-trailer trucks have an odometer on one hub of the trailer wheel. That's so that we can measure the distance that a trailer travels. The hub is weighted so it doesn't rotate as the tire spins, but it does contain a gear to count the number of wheel revolutions. This wheel has a diameter of 1.5 meters and it goes through 200,000 rotations. How many kilometers has the trailer traveled, or how many kilometers should the odometer read? Well, this one's pretty straightforward, although there are a couple things you got to be on the lookout for. The diameter was supplied to us as 1.15 meters. So let's recall that most of our computations require a radius, so we're going to divide that by 2. Secondly, the rotations of the wheel, if the wheel is going through a rotation, you can imagine that that wheel, if we were to cut that circumference and lay this line flat, that ends up being the distance that the wheel travels in a single rotation. So I'm going to identify that delta theta, that change in rotation, or I'm sorry, the displacement of our angles here. I'm going to call that 200,000 rotations. And since our unit of measure is radians for that, we need to multiply that 200,000 by 2 pi to convert that into radians. So then effectively, the arc length is what we're after here. Now, we have been talking about arc length as the radius of a circle times the change in angles, or the angular displacement. It just so happens that we're not doing a single rotation or a portion of a rotation. We're just doing many, many rotations. And that's totally fine too. The arc length, the length around the circle, or in this case, the length around 200,000 circles, is still the same. The radius measurement times the change in delta. So when we substitute the numbers in, we see a result that looks something like this. 722,000. Now, double checking over here, this measurement is a meter, so 1.15 meters times delta theta, the displacement, is a radian. Now, the radian is a scalar quantity. In trig class, I described how the radian was obtained by measuring the circumference of a unit circle, but as far as the unit itself of a radian goes, it's really just representing a portion of a unit circle, or a ratio of the length around the unit circle. So really the radian has no units to it in terms of our SI values here. That's a scalar quantity. A scalar quantity times meters leaves us with meters. So our answer here is reported in meters. I've just converted that into scientific notation once I kept the 3 significant figures. Used my t-chart to finish the conversion. If you didn't already know, we could just move our decimal 3 to the right. The act of moving 3 to the right, however, will simply reduce our exponent in our scientific notation by 3 values. So 7.23 times 10 to the second, or in other words, 723 kilometers for the 200,000 rotations. Number 5, Earth rotates once every 24 hours. What's the angular velocity of Earth? And if the Earth's radius is 6.4 times 10 to the 6th meters at its equator, what would the tangential velocity of the stationary observer be at that position? All right, so part A, we have a period of 24 hours per rotation. So there's our capital T. We might also think of that as a frequency. So if you thought of it this way, we have 1 rotation per 24 hours. That would be technically okay as well. But I'm going to use this formula here. If we're looking for angular velocity, that's our change, or our angular displacement over time. Now, our angular displacement is a rotation. 1 rotation is equivalent to 2 pi radians, which is our SI unit for theta. And our time value, our SI unit, is seconds. So I'm going to perform a quick unit exchange here. 24 hours times 3,600 seconds. Now, if we use the formula, 2 pi radians divided by 24 times 3600 seconds, we see that we have an angular velocity of 7.27 times 10 to the negative fifth radians per second. As a decimal, just a reminder, this is the decimal equivalent. So 0.4073 radians per second. Very slow rotation in terms of angular velocity. Now, if we take this a little bit farther in part B, we're looking for our tangential velocity. Now, what's interesting about our formula sheets this time is that the way we compute tangential velocity can be done several different ways, and you'll notice the same thing with centripetal force and centripetal acceleration. Because of our unit conversions and because of some of the complicated examples that we work through, it may be helpful to be familiar with all these different definition types. With rotational velocity, one of the most common methods that we use to calculate tangential velocity is simply the radius times the angular velocity. But with a little bit of care, we can see how this tangential velocity is also equal to our arc length divided by our change in time. So the length that we travel around the edge of a circle divided by the time that it took to travel at, that's also a measure of tangential velocity. And since arc length is simply the radius times our displacement, our angular displacement, we can use that definition to calculate tangential velocity as well. But in this case, I do like this definition here, that the radius of the Earth times its angular velocity that we just computed a moment ago is computed here. And with our dimensional analysis, we have a measure of meters and radians per second. Again, recall that a radian is a scalar, so it's effectively unitless in this computation. We have a meter times 1 over seconds, or meter divided by second. Meters per second is the measure that we're after. So that looks pretty good to me, and let's not forget a quick way to make this more reasonable for us in our class, in case you don't quite understand how fast 470 meters per second is if you double that, that's approximately the miles per hour. So I'm thinking of this as almost 500. So at the equator, even though we're only rotating at, what is this, 7/100,000ths of a radian per second, I think I got that right. We're actually rotating with a tangential velocity of 1,000 miles per hour if you were standing at the equator. So it's kind of an interesting dynamic there. All right, number 6. Oh, number 6 is an interesting one too. A rotating space station is said to create artificial gravity. And let's see here. Basically, we're in a tube and we're spinning that tube to generate centripetal acceleration. So if you're standing at the floor, that's where you would experience artificial gravity. The tube is 200 meters in diameter, and our job is to find the angular velocity necessary to generate Earth-like gravity at 9.80 meters per second squared. So this is what's happening. We've got this long tube, and we're imagining that if you're standing at the end of the tube and that tube's rotating, your body's inertia, trying to stay in a straight line motion, is affected by this rotation, and you're going to feel this inward force or this inward acceleration due to that rotation. So we have a diameter of 200 meters, which we'll call a radius of 100 meter. Our goal is to find a centripetal acceleration or inward acceleration of 9.80 meters per second squared. With centripetal acceleration, again, from our formula sheet, we've got lots of options to choose from. I think the one that I would like to use is this guy here, because we know the radius and we're looking for the rotational velocity. So r times omega squared, if we want to isolate omega, we'll simply divide by r and then use the square root. Technically, there's a positive and negative sign here since the square root wasn't present initially. So you can actually rotate in either direction. That's basically all that that's telling us. I'm just going to keep the principal root for this problem. And after we substitute in our values, we end up with 0.313 radians per second. Now, the unit analysis here is a little bit confusing at first. We have a square root surrounding a meters per second squared divided by a meter. Well, when you divide by a meter, that's the same as multiplying by 1 over meter, and we have this square root surrounding a 1 over s squared. If I square root of 1 over s squared, then I get a 1 over s. Now, that's not the unit for rotational velocity. However, if we recall that a radian is just a scalar quantity and effectively unitless, then in this case, in the context of this problem, we can reintroduce that radian without changing this unit. Now, 1 over s I like because we now have a radian per second reported. Some students and maybe even some textbooks would show that this unit as a second to the negative first power, or an inverse second. That makes sense mathematically, but as far as a description goes, I like leaving it in the denominator of the unit, and now we can say radian per second. All right, now the last one for this video is going to be number 7 here. With number 7, we've got a coin that's resting on the center of a turntable, like a record player. It's 15 centimeters from the center. The coefficient of static friction on the surface is 0.350. The turntable starts from rest, so it has an initial velocity of 0. It increases its rate of rotation, so the angular velocity is increasing. At what point will the angular velocity be large enough to allow that coin to slip? So in this problem, again, the radius is 15 centimeters, but we want to use that as a meter quantity. Our mu s is 0.350 with no units, and our initial velocity is 0, and we're looking for our final velocity. So I think the big thing to be aware of here is that our coin, this open circle here, is rotating with the record as the record spins. And because that coin is rotating, because there are forces preventing it from just simply traveling in a straight line, because it's rotating in that circle, there has to be some sort of center-seeking force restoring that pathway. So we have this centripetal force that has to be present in order for that coin to move in the circle. Now, the force that's responsible for that inner force is the friction between that coin and the turntable. So if I forgot to mention this, but this is the top-down view of this coin. So we're going down into the page here. That's the force that's preventing this slip. That's the force that's providing this centripetal force. So the problem here hinges on the notion that the centripetal force providing the circular path is exactly the same as the static friction force that's keeping that coin in place. Now we're going to assume that this turntable or this record player is laying on a flat table, so the force for static friction, or the maximum force for static friction, would be mu s times the mass of the coin times gravity. Now that's kind of interesting because mu s we have, gravity we know, but m hasn't been provided to us. I don't know the mass of that coin. That may or may not be a problem. But if I jump out to our formula sheet for the centripetal force, we have a couple different options to use. We have mass times centripetal acceleration. We can use this definition or even this definition. Now I know that our goal is to find angular velocity. This is the only one that contains that, so I think I'm going to use this definition here on the far right hand side, mr omega squared. So centripetal force is mr omega squared. And conveniently, watch what happens when we try to isolate our omega. We're going to divide both sides by m, and that quantity is going to disappear. We'll divide by r and take a square root. So omega ends up being mu s times g, divide by r, all underneath a radical. So that's helpful in that the algebra itself forces the mass to disappear, but in a contextual description here, it's important to note that the mass has no effect on this sliding frictional force in this particular scenario. So it doesn't matter if we're using a small coin or a giant steel weight in a similar situation. The as long as they're the same material, I should say, that's mu s is going to affect that. But it's the coefficient of static friction that affects the rotational velocity that we're about to see here, not necessarily the mass. So I thought that was kind of interesting. If we start substituting in values, we have a 0.350 gravitational acceleration. I like using 9.81. If you use 9.80, that's okay too. And our radius of 0.15 underneath the radical. Quick check here, mu has no unit. Gravitational acceleration is meters per second squared. We're going to divide that by, again, meters, and all of that's underneath the radical. And I think we saw something just like that a few minutes ago. Meters per second squared divided by meters does turn into a second inverse, or a per second. And if we reintroduce radian as our scalar quantity, then we can report our final unit as a radian per second. And off screen, I used my calculator and got 4.78 radians per second. And so while that's a good final answer, I just thought of something here. Records are usually played at 3 different speeds, 33 and a third RPM. There are 45s. And then there are also, I think, 78 RPM records. So if you know anybody that's into vinyl records, or if you've got a parent or a grandparent that recalls this from back in the day, I think those are the typical speeds of a record player. We can do a quick check here. If we're traveling at 4.78 radians per second, 4.78 radians per second, and then convert this to, let's see here, we've got 2 pi radians per rotation, and then we have, let's see here, 60 seconds per minute. If we use this T-chart to convert, let's see here, that comes out to be 45.6688 rotations per minute, or RPM. So this is kind of interesting. If we have this coin, and we know that it takes 4.78 radians per second to have that coin break free, that's our way of saying, well, it actually takes a little bit more than 45 RPM. If you put that coin on a record that's spinning at 33 and probably at 48, you'd be okay. The record that spins at 78 RPM, though, would break that coin free. The last thing that I'll say too, though, is that the 45 records are usually smaller than the 33 and a thirds. So I don't know if we have 15 centimeters distance from the center to the edge if you were to try this out on a 45. But you know what? It might actually work. I don't know for sure. 15 centimeters might be just too far for that small of a record. Anyway, I thought that was pretty interesting. Now I've worked through 1 through 7. Yeah, what the heck? I'll record a video for 8 and 9 as well, but I'll do that in another clip. Thanks for watching.